So we left off on this thing which we called the Poisson ANOVA table. It goes by other names. The Poisson deviance table is another name for it, and it's just a way of arranging the results of a lot of different models for the sake of comparing them. And a lot of different types of models were represented in this table. And the first one of the first interesting models that we talked about in the last lecture was this interaction model that had, for the skin cancer example, it was a model that looked at the effect of city, which was the exposure in this case, which city you lived in, Minneapolis, St. Paul, or Dallas, Fort Worth. And then there were age groups. There were 7 age groups, and then there was 7 product terms, these EW terms that represented the city by age kind of effect modification. And we talked about the way the rate ratio from this model was nothing surprising. It was the e to the beta plus the deltas. That formula here. And we talked about how this model had 16 things to estimate in it, 16 terms, intercept, exposure, and then 7 plus 7 here, 7 V's and 7 EW terms. And so that was 16 pieces being estimated, and that happened to be also the number of observations in the data set. Even though the data set represented the experiences of millions of people in two large metropolises, it still just had 16 observations that summarized those experiences. And so we had a situation where the model was saturated, 16 terms, 16 observations. And by the way, it was also fully parameterized. It had, for the 2 factors under discussion, city and age, it had all of the possible combinations of them, right? City, age, city by age. That's kind of it. So in this situation, it was fully parameterized and it was saturated. And as we talked about, this doesn't have to be this way. You could have, again, if you had multiple observations on the same age group in the same city, the sample size would go up, right? If you had 3 eras of observation or whatever it was, 3 alternative universes where you observed 20-year-olds in Minneapolis, and you had 3 observations, the saturated model would not have 16 things in it. The sample size would go up, and to saturate the saturated model, that's the model that has as many terms as observations, would have to go up. It would still be fully parameterized, though, okay? Because if you just measured, all you knew was city and age group, this is the most complex model you can do. That's it. It's not getting more complicated than this. It's just not getting more complicated. That's it. There's just 2 terms. And so the fully parameterized model would have 16 things, and the saturated model would go up. But in this case, they're the same. And we talked about that in the situation. We'll bring this up here. We have the deviance statistic is a statistic that we can reformulate to conduct likelihood ratio tests with. And it's the deviation from the saturated model. And so in the situation where we had a saturated model, the deviance from itself was 0, and that wasn't very interesting. But we can compare other models, in a sense, to that model and come up with interesting likelihood ratio tests that test hypotheses of interest. I'm going to skip through this. Okay, so here we saw this. This is what I just said out loud. That for this interaction model that happened to be the saturated model, its deviance was 0 because it is the saturated model. Not very interesting, but we can test those effect modifiers by dropping all of them and fitting the simpler model that just had city and age. And you would find something like this. You would find that the deviance statistic was 8.3, and that is going to be a value over the deviance over the degrees of freedom is 1.18. And we can use this information to conduct a hypothesis test of any significant interaction by looking at the difference of the deviances between the model with and without the city by age product terms. And what that looks like is this. It's the deviance of the reduced model minus that of the full, 8.26 minus 0. And again, it doesn't have to be 0. It just happened to be a saturated model. And you get 8.26. And if you're dropping 7 terms, between the reduced and the full, then you're talking about a 7 degree of freedom chi-square test. These things always follow the number of items that are being dropped from the model. So it's seven of these seven of these delta coefficients from the EW terms are under consideration for all being equal to 0. And you see that the probability on a chi-square 7 distribution, 7 degrees of freedom, of seeing 8.26 or greater is 0.31, as in this is not an unlikely value on this chi-square distribution, and you would fail to reject the null hypothesis. Okay, and you'd say, well, I don't really see any evidence here of interaction, and so we're going to kind of proceed and maybe drop all these. So, just small thing, but this actually, should make you feel a little uneasy, and we've done this throughout the course, but I just want to point this out. Notice here that we're actually dropping terms based on the acceptance of a null hypothesis, which is potentially a statistical no-no. Just throwing that out there. But this is how we proceed. Otherwise, you're stuck here, right? We haven't concluded. We don't have evidence of no interaction. We haven't proven that there is no interaction. We don't have enough compelling evidence to detect an interaction or an effect modification. If we observed 1 million more years of data, maybe we would detect an effect modification, right? Or if we had more information, it is actually possible that we would find something, or if we had a different statistical test or something else, right? We're actually failing to reject a null and actually acting on that, which is, it's in this statistical gray zone. But otherwise, you're stuck, right? It's very hard to prove it's very hard to prove that something doesn't exist. It's like a cardinal rule of science. You can't really proving non-existence of something is really difficult. Okay, and so too it could be that, if we observed another 20 years, maybe we'd find that effect. But we feel reasonably confident that, if we have a lot of data and we still, we have observations on a whole lot of people, and we fail to detect interaction, we can feel pretty confident in proceeding here. But I think just in terms of how, if you're, and how you present this information to external consumers, I think just keep in mind you're not concluding that there is no effect modification. It's really a failure to detect. So that's just, we're good at, you should become good at putting many, many caveats on your findings and explaining and counting things appropriately. And really, again, that I would just, I'm off my soapbox, but just something to keep in mind, because you may have heard from a sort of that's a pure biostatistician may have drilled, very much so that you don't ever conclude the null hypothesis, right? That's really not supposed to feel right. And that is kind of sort of what we're doing here. But again, this is just the art of how we do it. Otherwise, we're stuck. So we fail to detect interaction, and we're going to say, we're going to drop those and then proceed, maybe with the reduced model without the city by age effect modifiers. So we also talked about that same task, the same information here of comparing your model's deviance to that of a saturated model also is a goodness of fit test, as we talked about for logistic regression. And so any model compared to the saturated model, that the chi-square test of that difference also is the goodness of fit test here. And so just in this rephrasing of things, the null hypothesis is the model fits well, and the alternate is it doesn't fit well to the data. And so we'd have, again, a 0.31 p-value, which would say, again, supporting the null hypothesis that it fits okay. And right, that this Poisson model describes the information in this kind of holistic sense well. And to the extent that you're not including good things in the model, good explanatory variables, to the extent that the data just is not Poisson distributed, this is you're gonna have a very large deviance statistic, and you're gonna have a very small p-value. and you're gonna say, this is not really describing the data well, right? And this came up in the last lecture where we accounted for city, but we left out age, and age was highly explanatory of cancer. And so excluding age inflates the deviance statistic, and then you would just say, this doesn't describe the data well, objectively. So what's important here is that, in a sense, the interaction test is a two-model test, right? You got to look at the full versus the reduced. You're kind of, it's always this, you have to set up some comparison, some contrast. This has got these variables, and then this model is dropping them. The deviance statistic as used for the goodness of fit test is always a single model comparison. And right, you're comparing it to the saturated model in some big sense, but it's really just considering the model at hand. Is this model, this singular model, this model that has just city and age but no effect modifiers, is this one model a good model? And it's much less comparative than what we're doing in the likelihood ratio test. And here again, functionally, it's the same statistic and the same p-value, but it's not going to always be like this in life. And again, we would say, okay, yeah, this describes the data pretty well because we have not rejected the test. And the same caution about what I was saying about accepting a null hypothesis applies here. The null hypothesis is it fits, and the alternative is doesn't fit. And so here we say we have no reason to believe other than that it fits. But it could be if you observe to get another 100 years of data, you might see deviations, you might detect some deviation from the Poisson distribution, or just you have enough information to conclude that your model stinks. And then what? I don't know, you have to start thinking about alternatives. But again, it's this business of we have no reason to believe other than the null hypothesis, which is very different than the null hypothesis is truth. Again, same cautions apply here. So, we next showed how we can use the same kind of notions that we developed in logistic regression and survival analysis to assess confounding, right? So you can compare, if we had a gold standard model that was just city and age, we can drop age and compare the same hazard ratio, which is still e to the beta, between these two models, and rate ratio, not hazard ratio. You compare the rate ratio, e to the beta, in these two models, one with age, one without, and that would be the identical examination of confounding that we've been doing for the other model types, right? And that's what we showed here. And really 2.2 versus 2.1 from our estimate statements, and you really are in a similar place. So not, you'd say, we don't really think there's much confounding by age. And then this is where you have to kind of keep your eyes on the deviance as well, because, and again, you might want to do this in other regression forms too. You can have great control for confounding, but have a stinky model, right? So this is the model without age. And you'll get the right answer, but the model is probably not one you want to report because it just doesn't describe the data well. If someone else took your findings and used it for another application, what if someone, in 20 years from now when you're a department head of something in some place and someone finds this paper you wrote in grad school and it was you were interested in confounding and they were interested in prediction of cancer, they're going to take your junky model and predict cancer really badly because you reported the model without age. So don't do that. So I think we have to, even though if this was your objective was confounding, I think it's really important to keep your eye on the whole picture and do the other diagnostics and keep on top of whether this is a model that's worth disseminating to others, even if you get kind of the right answer. So just something to keep in mind, we didn't emphasize this as much when we were developing logistic regression, maybe because we just showed goodness of fit at the end, but you really could have the same situation with our logistic models, right? You do all this great stuff, you have the best EVW model, and in the end, the Hosmer-Lemeshow test, let's say, would show that the model actually just doesn't describe the data well, right? Or alternatively, maybe you made an ROC curve that showed low predictive power. So you discovered an interesting pattern, but maybe the model just isn't very useful. I mean, that doesn't necessarily rule out what your findings. It doesn't necessarily mean you've done a bad job. You may have accurately explored, the ideologic association that you care about, but just this helps kind of, color your findings when you also, by the way, your model doesn't predict the phenomenon very well. Sometimes it makes sense if you're studying obesity, right, or something very complex with a very complex landscape of determinants and social determinants and genetic and so forth, and you're studying one little aspect of that, you may actually, in that case, be in a situation where you can get an unbiased, a minimally biased estimate of the association of that you're interested in, but you maybe can't explain all of obesity, and maybe that's okay, right? Because no one study is going to explain all the thousands of determinants of obesity. So there are situations where these can be in different places, but just keep in mind that you really need to monitor the goodness of fit, and in the case of logistic regression, there was also this extra piece of predictive power through the ROC curve. And really, what makes a model good is all of it, unfortunately. So you have to do everything, even if this is good on the confounding front. So I made your life more complicated. I'm sorry. And this is even a little more complicated here, was we even talked about some alternatives here for considering age. And what was the point of this? We discovered that, if you plot on the log rate scale, the log of time versus the log of just the unadjusted rates kind of appeared linear. And we thought, well, maybe we can take advantage of this association by turning age from a categorical thing into a continuous variable, and then fitting a single term in the model for just log of age rather than 7 dummy variables. So why would we do this? I think it looks like a necessarily complicated activity. I think what's nice about this is you now can you're not fitting a saturated model anymore, so you have kind of more statistical power, right? You're estimating less, and you have just 3 things in your model rather than with the no interaction model you'd have 9 when it was categorical. You'd have 9 terms. So it's a little more simple. It's you're using up less of your statistical degrees of freedom, as it were, in you're estimating less. And the other piece is that when we were looking at age previously with the categorical variable, it was totally unordered. Like, is age group 2 at more or less risk than 3 versus 8 or whatever? It was just 7 groups in a bag, completely unordered. When you fit when you fit this continuous term, you're actually imposing a structure, which we believe exists. There's this log linear kind of thing here, where on the log scale it's linear, and so there's a structure that we're putting in place, but it lets us make statements like, for every X amount increase in age, the cancer rate will go up by this. Right? It lets you actually talk about the age pattern in a single coherent way. And in fact, here, we didn't really show it in the slides, I guess. If you exponentiate this is going to give you the rate ratio for every increase in the age group. So this is going to give you the rate ratio per 10 year. I forgot. However, this is scaled funny, but on the scale of this variable, this is this log t business, it's going to be on this t scale. But basically, it's going to give you some sense for every X unit increase in age, the cancer rate goes up by this much. And that's actually nicer, it's a nicer soundbite, an easier thing to convey than, hey, I fit 8 age groups and there's 7 dummy variables, and here is all the group-wise kind of relationships, and you're going to have to describe how this mixed bag of unordered ages behave. To have a single continuous variable is really nice, because then you get to describe the rate per some unit increase. And we saw this with odds ratios as well in logistic regression that if you fit an odds ratio if you fit an odds ratio with just a continuous variable, it's now describing the increase, the relative change in the odds for some unit increase on the continuous scale. So that's nice. Obviously, again, when you fit continuous variables in any regression model, it comes with more stringent assumptions than the dummy variables, because now you're really saying that this is on this scale, linear, natural log of the rate, this linear model for the natural log of the rates, that the log of time is, log of age, time, whatnot, is linear on this scale. And that's potentially a really strong assumption, which may not hold, but it actually, in this case, it actually appears to hold pretty well. And again, how do you know that this is it, right? Someone magically gave you this, and we got lucky, right? But in order to divine what is the best way to include your continuous variable, you're going to have to make plots or have some kind of a priori knowledge, ideally, or people just put a continuous variable in the model, and you just hope. Please don't do that. If you can, making interesting plots like this, unadjusted log of rates versus log of age, is one way to explore the use of continuous variables for Poisson regression. So in this model, we saw that basically it gave the same answer as when age was considered as not continuous, as this categorical 8 age group thing. Right? This is basically the same exact rate ratio. And also the model similarly fit well. So we know that we need to include age in the model in some regard, and including it with this log of t term gets us a good fitting model. 1.1 was the value over degrees of freedom, and we said that this is kind of the shorthand way of doing the chi-square test. Basically, if this is in the neighborhood of 1, it's going to fail to reject the chi-square test for goodness of fit, and that is the case here. So again, we could, just like we tested age before, we can look at a model. We tested age by city interaction before. We can test that again in this model by having beta, the EW term, that's exposure times log of t, and we can again test the deviance between this model and the model that had that product term. And actually, we can I'll just jump to here. We can do that by running we can do that by running the models and just lining them up here and looking at and doing that test while examining this table here, which is the Poisson ANOVA table. And the point of this table is for conducting hypothesis testing and making just kind of conclusions about what Poisson model is good. And it's just a shorthand for managing some of this deviance information. And so the deviances are in this column. And again, like just your eyes should be drawn to something like 2800 is probably not a good deviance, no matter how you cut it. Like this is a bad model. And why is it a bad model? It has just the intercept. Okay, and the intercept is the model of every group has the same rate. It is a constant. It's 20 or whatever it is. Every group has the same rate, whether you're in Minneapolis, Dallas, old, young, whatever. We're going to say the same thing for you. So it's just this flat line model, and that's a bad model because it doesn't explain the variation in your data well. Right? So it's just fitting effectively a constant rate. Not a good model. Right? And as you add things to the model that are informative and interesting, the deviance gets smaller. Right? So you added city, and look at that, deviance goes down. And obviously, where you really get the bang for the buck is city and age together, and that's where you get the small deviance values. So again, this is really like almost in a sense, if you remember sums of squares error and mean squared error from linear regression days, maybe, sort of. That was this piece that was about how much is effectively unexplained in your model, and that's going to go down. And the more that your sums of squares regression goes up, the more the sums of squares error goes down. There's kind of this tug of war. It's the amount that you explain versus don't explain. And the deviance, in a sense, is this analog to the sums of squares error. It's how much you can't explain. And just like in linear regression, all of your statistical tests relate to that quantity, the sums of squares error and the mean squared error. All your denominators to the hypothesis tests in linear regression were about the mean squared error. That's very similar to the deviance, where we're going to use this as this is the quantity of what's explained versus not explained, and that's very similar here in Poisson regression. This is the analog of the mean squared error in some sense. Maybe this is the analog of the mean squared error, but this is the sums of squared error. I'm making this up a little bit. I'm drawing analogs. I'm not making it totally up. It's grounded in the same concepts. This is just, there's no least squares estimation here. This is not least squares anymore, so there's no sums of squares error. But this is the analog in a sense to that. And so, here on the bottom two rows we have a comparison that we set up earlier. The bottom row is the model that has 16 terms in it. It's the saturated / fully parameterized model that had age, city by age. And then above it is the model without that product term. And so what you see here is we see 16 parameters. The deviance was 0 because it is the saturated model. And this is the degrees of freedom for the deviance test here, the deviance goodness of fit test, and it's also 0. How do you get this column? This column is the number of observations minus the number of parameters. Those is a nice happy relationship where this column and the number of parameters adds up to 16. So when you're doing the goodness of fit deviance test, it wasn't on the slide here, but on the slide for that test, but I'll just say it now. The degrees of freedom for that goodness of fit test is this column. It's the number of observations in your data set minus the number of terms in your model. So if you have 9 things in your model, 16 minus 9 is 7. And that's the degrees of freedom for the deviance test for goodness of fit. It's the amount of things you have to drop from the saturated model in some sense in order to get your model. And so so parameters in your model plus this degrees of freedom will equal the number of observations. That's another way to say that. So what you can see here, if you just compare these two models, you can do your likelihood ratio test for interaction. That's the 8.3 minus 0, right? So this is the deviance of the reduced model minus that of the full. And that is also a 7 degree of freedom test by coincidence because the comparison model, the full model was the saturated model. Anyway, you can just look at this. You can very quickly say, okay, 8.3 minus 0, chi-square 7, do that test. And you can do that pretty quickly, and you'd say no significant interaction. Here's 2 other models, right? This is the top one is one we actually showed output for. We didn't show it for the bottom one. The top one is the log of continuous age model, and we saw, okay, first of all, it has 3 parameters, alpha, and then we're using theta here. Again, there's no reason to, we could have called it gamma. It's theta. And again, this is what the book says. That's why it's on the slides. So it's theta, and then there's the beta times exposure. So 3 things in the model. Deviance is 14.6. So 16 minus 3 is 13. This is the degrees of freedom if you were going to do a test of this model versus the saturated model for the purposes of goodness of fit testing. So you do a 13 degree of freedom test, okay, and you would get that this actually fits well, and you would fail to reject that test, and seeing a deviance over degrees of freedom of 1.1 kind of tips you off to that. Now this model below it has this extra piece, which is the delta times exposure times log of age. This is the product term for city-age interaction, but now considering the interaction in a continuous kind of way. This is this has 4 parameters, right? This is a 4-parameter model. Notice the other way to do this with categorical age is a 16-parameter model. This is nicer, right? We're not saturating the model, and we're going to get basically the same explanatory power. This is nice. We only are estimating 4 things. Deviance was 10.6. So now 12 is the degrees of freedom for the goodness of fit test. 16 minus 4 is 12. And you see, again, this one of good fit. Okay, so these are the degrees of freedom relative to a saturated model. If I want to test, hey, is there a significant effect modification when I'm thinking about continuous age? It would be the chi-square test that is subtracting the reduced 14.6 deviance from, you're taking away 10.6 from that, the full deviance. That's about 4. The degrees of freedom for this test is not 13 and it's not 12, it's 13 minus 12, right? It's the number, which is effectively 1, which is effectively the number of things that we've dropped between the two models, right? So it's also the same as 4 minus 3. You could get the same answer by subtracting either way. And these degrees of freedom on their own are telling you about the degrees of freedom for the goodness of fit test. To do the chi-square test, the likelihood ratio, deviance, whatever you want to call it, test, that is comparing the two models to each other, it's the difference of these things that gives you the degrees of freedom for that test. So here it's chi-square with 1 degree of freedom is what we're talking about because we've only dropped one term between these two models. And the cut point for the chi-square 1 with alpha 0.05 is 3.96. This should just be one of those, let's just know it. And then so this, actually it's 3.86, I think. Come to that thing, 3.1. Anyway, we'll have to fix that. But 4.0 is larger than that. And so but this would still be kind of marginally statistically significant. We can calculate what the p-value would be like 0.03. And so it would be it wouldn't be a wildly significant result because it's kind of on the border of the cut point, the alpha 0.05 cut point on the chi-square 1. But you would conclude statistically significant effect modification interaction, whatever you want to call it. Notice that was a different result than this, right? So this is, again, where truth is hard to divine here, right? Maybe you have less power in some sense because age is considered unordered here, right? You're not harnessing all of the information in the age groups to detect this pattern across ages, and this is just a unordered age model. This is estimating a whole lot more. And you might just say, this is maybe a weaker way to represent the information in some way compared to this, which is actually harnessing the continuous age data, and it's actually there's less of a burden. You're estimating less stuff, and you're just comparing one term. Here we're statistically testing 7 terms. Here we're just statistically testing 1 term. And maybe that test of one thing picks up the interaction in a way that the test of 7 terms does not. Maybe. Again, you can't look at it and say that is what's going on, but that would be my intuition of this. Like, yeah, of course, it was continuous. You were able to use all that information. Again, this always comes with the caveat if the log age, log rate relationship is appropriate. If it's an inappropriate way to model the continuous information, then it could be statistically significant but wrong. That happens. But it looks that graph has convinced me. Anyway, so what's cool is that doing this log age thing had a lot of advantages. It's a single number to describe the relationship. It also maybe actually gave you extra statistical oomph to detect the effect modification. Yes, statistical oomph. That's a real thing. Okay, so here is the comparison. Here's 2 models. They both have categorical age, and then one has city and one doesn't. This is the model, this is the comparison that's perhaps useful. It's an odd model. It's useful if you'd want to assess whether, it's important for assessing the effect of exposure. I'm sorry. Why would you make this comparison? This is the test of whether exposure is significant, whether city is significant, right? Imagine if you determined age as a confounder, got a control for age, and let's pretend this is my gold standard model. One of the last tasks that you might want to do in your analysis is now say, great, controlling for age confounding, is the effects of city significant? Right? That's like maybe why you did the study. You want to know, is there an actual difference in age-adjusted cancer between the two cities? And that is this comparison, right? It's the model with and without city. And you're going to do a likelihood ratio test of the city effect. It doesn't actually show that here, the computation. It's going to rate the test of, hey, is there a significant city effect, is going to be 268 minus 8.3, and that's a chi-square 1 degree of freedom test, right? This is the deviance of a reduced model without city minus the deviance 8.3 of the model that has city, the full model. So this difference, right, it's going to be 260.1, right, is going to be the test statistic, 260.1, chi-square with 8 minus 7 or 1 degree of freedom. That's remarkably significant, very, very tiny p-value. And that would be the test of significant city effect. And again, that's probably going to be one of your take-home messages. When we adjusted for the age distribution being different between Minneapolis, St. Paul, and blah, 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 we were still able to conclude that the cancer rates were different between the two cities. So that would be this comparison here. And you see it's basically consistent with the analogous comparison with the continuous age model. So, right, I mean, it's very, very, very similar. You're going to get highly, highly significant city effect, regardless of which approach you took. So you can do a lot of cool different things here. Like on this one table, we've compared a whole lot of different types of models. We're looking at goodness of fit. We're looking at tests of effect modification, tests of the exposure itself. This one thing that doesn't quite represent is the confounding assessment piece, right? Which we're, because we're not showing the rate ratios here for exposure. You can imagine adding some columns, at least on a no interaction model or something. You can make some interesting columns here where you track what happens to rate ratios, and to do confounding assessment. You can expand this comparison if you wanted to. But this is just kind of a standard table that people make for describing the results of Poisson regression statistical tests, at least, not necessarily confounding. So that's kind of cool, Poisson ANOVA table. And again, it's not really ANOVA at all, but it feels kind of like the ANOVA table, which is that table that has the mean squared error. It has the sums of squares, mean squares, p-value. This is my middle of the air ANOVA table. That's that first thing that comes out of linear regression that shows you all of the components of the linear model fit. Kind of the basic table for linear regression. One piece here to keep in mind is that when we're doing the deviance tests, the likelihood ratio deviance kind of comparative test, there's this requirement that the models be subsets of one another, right? You have to be dropping down potentially, though in some way, as most of the time, let's just say, because you can maybe make an exception or two. We can talk about that if you want. But in general, the models have to be subsets of each other. One has to be reduced relative to the other to the full model. You have to be dropping down things here. So in this case, these are two models that they both have city and they both have age. But they have age differently. One's the continuous age, one's the categorical age. And so, can we test that in some way? Can we test whether one's a better model in some way than the other? And the answer is that it doesn't quite make sense, because one's not a subset of the other. You can't say, okay, when I drop this term, I wind up with the other model. And so you can't directly test one deviance versus the other and say, yes, better model, go with this one. We have obviously a lot of other circumstantial evidence that makes us feel, I think that makes us feel pretty good about using the continuous age model, but there's no direct comparative test here. But what we do have is this information about the deviance from a saturated model. So if you imagine you had, one of these had a really bad deviance, high deviance, and this deviance over degrees of freedom would also be high, you'd say, okay, yeah, we have one model that fits well and one model that doesn't, and you could look kind of independently at each of their fits and say, one of these stinks, let's not use it. And that's clearly a good way to, I mean, it's a way to assess which one to go with. The same issue came up with goodness of fit and logistic regression. We talked a little bit about this too, where each one is comparing to a saturated or some ideal model, but you're not comparing models to each other. And so again, it's the same thing. You say each of these is being compared to the saturated model, and one of them, if one of them was really as good at fitting the data as the saturated model and the other one stunk, you'd go with the one that was good. So they're being kind of compared to some external referent, not to each other. They're compared to the saturated model. So anyway, so we can't directly statistically test it, but use the deviance and the deviance over degrees of freedom to guide you towards the better model choice. That's kind of so that's kind of the big picture there. So okay, so the skin cancer example, let's kind of put this one to sleep. We've talked about it a lot. It seems like the model that has no effect modification, right, we said no significant effect modification, or maybe marginally significant when we thought about age as continuous. But it seems like very possibly the no effect modification models are reasonable. When you consider age as either categorical or continuous, they both seem good. They're both reasonably fitting well, right? 1.1, 1.2. You get the same estimates for the rate ratio, the confidence intervals. It was up there, but we didn't harp on it too much. But the confidence intervals were the same width also. They both seem good. Maybe you go with the log model for the maybe because it has a lower deviance degree of freedom. I mean, it's 1.2 versus 1.1. It's not, not a big deal. There's no like magic rule of thumb, by the way, for like, if the deviance moves by this much, if it's within this amount, it's okay. But 1.2 versus 1.1 feels basically the same. But maybe you'd say the log age one is better. I just think it's simpler, I think for the reasons we talked about, that having a single thing that describes the age relationship is just easier to present, easier to talk about. When you're on CNN, you can say like, for every, just so you know, when you move to Dallas, for every 10 year, you can have your like single soundbite to describe the relationship, and that's what you'll say on TV. So I think there's just the simplicity of the message is nice. I mean, we have we're here talking about statistics, but I think it's also important to talk about like how you frame this, and if you can get something around a simpler message, that's actually better when you communicate with the stakeholders. So I think we would say there's a significant effect of city controlling for age. Right, being in Dallas, Fort Worth seems to, at least just from this surveillance data, seems to imply about a 2.2-fold higher rate of skin cancer relative to being in Minneapolis. Right, it's a very ecological thing, right? Is it the people who choose to live there, or what the genetic makeup of Dallas residents, or is it the sun? I think the implication here is the sun. And that it's that controlling for age, that you're at this 2.2-fold higher risk for acquiring cancer in the city. And here is the confidence interval, 2.01 to 2.47. So we did a whole lot of workup and considered a whole lot of different models, and what we get is 2.2 is the relative rate. Any questions before we jump to something else? Okay. Very well. We'll jump to something else. So it turns out that the Poisson model is great when it works, but sometimes it doesn't work. And mostly because that processes that should behave Poisson sometimes don't, just because reality sets in, and you feel like you should have this counting process, rates, clean rates behavior. But there's often outliers in Poisson processes. And the Poisson model, remember, had this has a strict assumption that there's a single parameter, mu, which dictates the mean and the variance of the Poisson distribution. Okay, so you can't have, this is really stringent in terms of how the data is described. There's one magic number that describes all the data. When you think about other distributions, like the normal distribution, you have two parameters. You have the mean and you have the standard deviation, or the variance, right? The square of that. And when you have two parameters, This actually, in some general sense, gives you more robustness to deviations. Like you can have your data, you can have many situations, like with the normal distribution, you can have many populations with the same mean, but very different variation around the mean, and you can estimate the mean in all of those groups and get the same answer, right? In some sense, right? You have different populations that each have a mean of 10, but they're very different variances. You could control for population in a model and fix the variance problem and estimate the mean reliably across very different populations with different, they all have the same mean but different variance. So having two parameters is actually really helpful because any deviations in the data distribution can be controlled for and you can still estimate the mean. Problem with the Poisson distribution is when the variance goes wacky, your estimation of the mean goes wacky. And when we are measuring the rate ratio or the predicted rates, we're talking about means, right? We're trying to estimate the mean effect in the population. Where we're talking, what's the mean skin cancer rate in Minneapolis is what we're effectively, when we're looking at rate ratios, we're talking about the mean behavior in the population. If there's weird variation in the data, it's going to bias horribly our estimate of the mean and the rate. And it's because of this dependence on the mean and the rate. They are the one and the same, and outliers that in the variation of your data will mess up your mean. So that's a problem. And it's a problem because, again, the data just often don't behave perfectly Poisson, and you'll get outliers. And I don't have a good natural way to motivate that, but it just, here, this is just an image from the internet of an overdispersed Poisson distribution. And so what you see in this is, I bet it says number of days absent, I don't remember the example anymore, but the point was that here, you see some outliers. This little tail should not be here. If the data was truly Poisson, it would kind of extinguish faster in some sense. And then often in real-world Poisson data, we get counts that are kind of out in the right tail here. And that might be, if you're thinking of skin cancer, maybe it was a really sunny year or whatever it is, or there's some subpopulation that you didn't detect that has has a high amount of cancer that skews things right. And even if it's a small amount, it distorts the variance, and that distorts the mean because it's Poisson. There's little robustness to that deviation. If it was a normal distribution, linear regression thing, there's actually more robustness because the variance can get inflated and your mean may not be too biased. In Poisson, it's exactly the one and the same. And so little deviations, little irregularities out here in the tail that you didn't model, if you had, what if you had some highly at-risk subgroup and you didn't include them as a term in your model, you're stuck with them as outliers, basically, right? Does that make sense? You can't account for them, you can't model them. There's this interesting ethnic group that lives in Dallas, and they all get skin cancer, and now they're all out here, and you don't know about it. You're going to observe this tail of variance, these very high people out of the tail, and it's going to distort things. This is called overdispersion. The dispersion of the data is beyond what you'd predict, or beyond what it should be. That you have the variance is more than what it, the true variance is really more than what the true mean rate is in some sense. That the mean rate is somewhere over here and it's being pulled to the right by this dispersion out to the right. And this honestly happens quite a lot in Poisson, with Poisson data. Less so perhaps when you look at surveillance data and some of those big population level data sets, but more if you're modeling a smaller, if you're modeling horse kicks, there's just going to be some people that get kicked a lot or whatever it is. There's going to be, the more micro the process, this is just a general kind of thing, the more smaller the process, the more these individual outliers might show up, I would say. And so what do we do about this? How do we detect it, and what do we do about it? Is kind of the two pieces here. One piece is actually by looking at your deviance over degrees of freedom, and the other way to do it is by looking at residual plots. So basically, if you have a good model, and this is hard to say, but if you have a model that you feel has all of the right variables in it, and yet you're still seeing very, very high values of the deviance over the degrees of freedom, then that could suggest overdispersion, that the model's still somehow not fitting well. You have bad goodness of fit, right? You have bad goodness of fit, even though you're fitting a Poisson model and you have all the right 10 variables in it, and it's just off the charts bad. That could be that you have overdispersion. And probably a better way to diagnose it is through the use of residual plots. So residual plots are, you can get them from any statistical modeling procedure, right? And do you remember the residual plots are the plots of the residual error from all the points in your data from the predicted mean value. And it's those bands, it's those bands that we make these residuals, and it's a flat line, and there's these bands of two plus or minus 2 standard deviations, and you're looking at kind of a pattern. Remember, in linear regression, we're looking at patterns in those, and different, like a cone pattern meant that the variance was getting bigger, and weird pattern this way meant that you were there was curvature in the data that you weren't detecting, and there was different stargazing that what happened for linear regression. When we do this for Poisson regression, the pattern to really look for is just outliers, really. So points that are out of the plus or minus 2 standard deviations bands. I didn't make an example of this. See it. But it's going to be, here, I'll just go over here. You're going to make a residual plot from GenMod, and it's going to show something like this. It's going to say, here's the 0 line, and you're going to see, here's plus 1, plus 2, minus 1, minus 2, and you want to see just like a nice, happy containment. 95% of the points should be between plus or minus 2, but if there's stuff like way out in plus 4 or minus 6, that's showing you that there's at the value of let's say it's your y, it might be your predicted y's is on the axis here. At some value, you're just getting way crazy counts that are way out, and this group has a very, very high count or rate. Then there's this interchange with the count or the rate, but there's basically data that's, the observed data is way out of range from what the model predicts. It's 6 standard deviations out from what the model says it should be, because there's this subgroup that seems to always get cancer and you haven't modeled them. And so you're going to see points way, way, way out here, and that's going to suggest overdispersion. It's less about finding like a pattern, so remember, like in linear regression, that doesn't work. So in linear regression, there's you would see pattern. This is the cone pattern that I was talking about. In linear regression, you see this. This means that the variance is increasing with bigger values of your data, which means you need to log transform usually. You're not doing this so much with Poisson regression. It's really looking for very out of range residuals. And they may increase, they may get more out of range at more extreme values of your data, or maybe, but it's really just looking for that out of rangeness. And that would suggest overdispersion. You can also get underdispersion too, which is going to be too tight of residuals to this plot. You're just, you're seeing mostly that, oh, this doesn't work still. You're getting mostly this kind of pattern, very tight dispersion, and you should see more variation in the data. But the more common thing that you get is this overdispersion, because the Poisson assumption is so stringent and stuff, it's not robust to bad stuff happening. And so, again, if you think your model is good, but yet you're still seeing this bad residuals, high deviation from bad goodness of fit, non-good fit, I don't know, there's no good way to say this, then you probably have overdispersion. So what do you do about it? There's 2 things you can do about it. You could basically tweak the model, the Poisson model, and you can flub your way through it. So there's the flub your way through it. But this might be indicated in certain situations. So there's ways to force it to fit. That the flub way through it means force the model to fit anyway. Or you can actually choose another modeling technique. Makes sense, right? So you can either try with the Poisson or you can go to something else. And the something else that's usually used is called a negative binomial. It's called negative binomial regression. And it's a different distribution altogether, and we'll talk about that. But it's very similar to Poisson regression. So the fake your way through it approach is using this thing called the scale parameter. And what it does is it introduces a little tweaking term here that instead of setting the variance equal to mu, it puts a little multiplier in here that imposes a different relationship rather than 1, like mu times 1 equals variance. It's going to put some other little correction factor in here, 0.6, 1.2, whatever it's going to be, and it's going to basically put this fudge factor in here, and it's going to make it work. So what you'll see, you're going to always get an answer. This will always work. But the problem is if the data is really, really not Poisson and you're making it work this way, you're just basically patching a problem but not really doing good science. And so I'll show you what I mean by that in a moment. And this can really be used for over or under dispersion. This can be used for either of these. But again, if you need to tweak this a lot, if you need to scale it by a factor of 100, if your variance is 100 times the mean, that probably means you're not doing you shouldn't do this. Like Poisson regression was not a good idea because you're really forcing a huge peg into a small hole or something. I don't know, some kind of square peg. I don't know, something. It's not working here because you're forcing the variant. It's just not going to work. So what are we going to do about it? So we're going to. This is what it looks like. Here is a model. This is the skin cancer model again. So this is maybe a model that actually has good fit. Here, remember we talked about this thing on the bottom here, scale. The scale parameter is what we're talking about here, and it's this piece that is going to change the variance relative to the mean. So normally when you run Poisson regression, it looks like this. It says scale is 1. Why is it 1? Because it's 1 times mu equals variance. That's why it's 1. It means we're assuming regular old Poisson. Over here, let's say you concluded from your residual plots or from the deviance degrees of freedom test type stuff that your model had bad fit and you want to try scaling it to work. What you do is you add this option called descale. And what descale does is it finds a value of k that makes the data fit better. And I'll show you what I mean by better. And what it does here is it recomputes everything and it fixes the variance. It's fixing the variance basically to make the Poisson assumption work. And it says 1.0862, which by the way is the square root of k, so it's the square of this is the correction factor to the variance. This is the magic number that makes the data behave perfectly Poisson, okay? So right now, at 1.0, it's not perfectly Poisson. There's some dissonance between the mean and the variance. That's actually the deviance, is that dissonance. And so at 1.0862 is the magic number that makes it work. And I'll show you. I'll show you what I mean by makes it work. And at this magic number, this correction factor to the variance, the data are perfectly, beautifully Poisson. Okay, and so what that means is the mean values don't change. Notice between these two models, the beta terms, the mean parameters being estimated in some sense are the same, but the standard errors change because that's the variance is being corrected to make it more Poisson-y. I'm making up words here. So but basically you're adjusting the variance to, so this scale thing, these values are all these standard errors are all 1.0862 times the top ones. They should be. Or if you square it, the variances are the square of this times the top one. So this is a correction factor that is globally applied to every term's variance or standard error in order to fix the Poisson problem. And that's reflected actually in the two summary tables for the Poisson goodness of fit stuff that's kind of at the top of GenMod. And normally, you see these first two rows. This is deviance, this is our old friend, then it says scaled deviance. Scaled deviance is what happened after I used descale, okay? And the default value for d-scale is 1, or scale is 1. So these two rows are usually the same because the scale factor is 1, and it's the same, it's 1 time, it's the same thing. So that's not very interesting. When you use d-scale, things happen. It shows that the deviance is equal to 7. Okay? After it's scaled the deviance, it's equal to 7. Notice 7 over 7 degrees of freedom is 1. This is perfect fit. It forced perfect fit. So you can't actually do a goodness of fit test on this other model because by definition, it's kind of like forcing it in to make it fit. And so by scaling all of the standard errors and the variance and all of that. So this, in some sense, fixes the problem of overdispersion by forcing everything to work. And it adjusts all the variances, and it's great. Notice that 8.26, so 8.26 divided by, let's see, there's a relation. This is 8.26. To go from there to 7 is, again, it's applying the same. It's the square root of this. This is the k factor. Basically, these differ by this factor k. That's, again, how you get from 8.26 to 7, is by you have to divide, I think. I need to whip out my calculator. 7 times 1.8 should maybe give you, 1.18 should probably give you 8.26. So, again, there it is. Okay, so right, so this is moving exactly by that k factor. Is how you get from here to here, from deviance to scale deviance. It finds this magic number, and then it perfectly applies it to all the standard errors. So it's this magic single number that fixes everything. Except that you should be wary of a magic single number that fixes everything. So this is making it work. It removes maybe minor deviations from the Poisson by finding a little tweaking factor that makes it fit a little better. But you haven't, first of all, this model is now automatically fixed. You can't even test goodness of fit anymore. But if this model really stunk, if it had a value over the deviance over degrees of freedom of 20, 200, a big number, you could always find that magic constant that returns it exactly to, in this case, that would return it to 7 and give you deviance over degrees of freedom of 1. There's always going to be some constant out there. It might be dividing everything by 200 or multiplying it by 200, whatever. It's going to be some big correction factor. And the question is, like, whether you fixed the problem, but did you really, you made the numbers work, and you made the goodness of fit better, but you may have still been fitting a junky model. So this approach is basically for fixing small deviations, maybe. I would say, like, if you really want to go that extra mile, and you saw value over degree of freedom of 1.8, let's say, or 2, or something where it's maybe a little more of a deviation from 1. And if you apply this little correction factor, it kind of rounds the edges, and it's more Poisson-like, and maybe you feel okay with that. But it's really where it's like egregious, flagrant, Poisson doesn't work. Don't do this because you're just really not doing a good job. So don't do that. So when you see the more egregious errors is when you would consider a negative binomial regression, which is really saying, actually, don't do Poisson regression. Poisson doesn't work. And the beauty of negative binomial regression is that it's a very conceptually similar distribution to the Poisson model, but it has 2 parameters. It actually has this kind of scale, has a second scaling variance-like parameter in it. Like the normal has 2 parameters, and it doesn't require mean equals variance. It already has its own extra scaling parameter built in, and it's a distribution that's maybe more favorable to use. It's very similar conceptually to the Poisson and the binomial. It's the count. It classically describes the count of failures until a success has occurred. Okay, so remember the binomial distribution is just the count of successes. It's determining the binary, the sum of different binary successes, and then it's the distribution of those binary successes. The Poisson distribution is the count of successes, rather than describing the different successes themselves, and then the negative binomial is the count of failures until the first success has occurred. So for example, what's the probability of getting five tails before you get ahead? Like if that was your question, then you want the negative binomial distribution, right? So it's number of failures till first success is the negative binomial distribution, rather than what's the probability of getting 5 heads or 5 tails, which is the binomial. And it often works well when the Poisson model is overdispersion. It's basically the idea that it's another counting process type of distribution, and it tends to skew more right, basically. And it also has a scale parameter built into the distribution that you can estimate. And so, that's spelled wrong, Jen owned. So what's great about it is it's really easy. You don't have to do very much else in SAS. It uses a log link, just like the Poisson, but you switch out the distribution to be negative binomial with neg bin here. So this is going to be the only thing you change, and now you're suddenly fitting a negative binomial regression model. So here is the same model, again, the skin cancer model, fit with Poisson on the top, and negative binomial on the bottom. And what you'll see is everything's very similar. So here's Poisson, here you can also write NB. As SAS, you can do everything 20 ways. So here it doesn't say neg bin, it says NB for the distribution. The parameter estimates are similar, not exactly the same, but they're pretty similar, and honestly the variance estimates are kind of similar too. This is probably because there was not much overdispersion to start with. So you're not even fixing much of a problem, frankly, by fitting a negative binomial model. But notice this is scale parameter 0. This is an unscaled original Poisson model, nothing special here. This says dispersion. This is the dispersion parameter of the negative binomial. This is that extra parameter that negative binomial is estimating. And so here, basically you are getting this is a model that is more robust to deviations, to these overdispersion deviations. And so this is an alternative model to consider. One piece here, notice this says warning, is that the negative binomial distribution is a bit more data hungry, partly because it has to estimate an extra parameter, and just in general, what you'll get is some warnings that basically you may not have enough. This is basically say the model may not be converging. I'm not so sure I trust these estimates. That actually they look pretty similar, so I trust them. But SAS is giving you a warning that you only have 16 pieces of data, and you're estimating a dispersion parameter to intercept a city and then 7 age groups. SAS isn't happy about that, and that's when it's not happy about convergence issues, which is often because you're fitting too much relative to your data set, you get warnings like this. So you didn't get it with Poisson. So this switch to negative binomial created this data requirement that SAS isn't happy about. So we fix some problems, we create more problems. That's kind of what we do, and there's never like one silver bullet that fixes all the problems. So that's the negative binomial distribution. And there's another family of stuff which I wonder actually if we have extra time in 2 classes that we'll get to, is talking about zero inflated Poisson, which is another situation that you see where the Poisson model doesn't fit, and it's because you have too many zeros. And that happens really when you're looking at individual counting processes. So for example, if we're going back to horse kicks, in some groups they're just, they just never walk behind the horse, and there's all these zeros. And so when you have an abundance of zeros, but otherwise the data is Poisson, you can model the data with a 2-stage model that basically models the 0-1, like 0 kicks or more than 0 or non-zero, and then once you're talking non-zero, it looks at a Poisson model. And so I want to see if maybe we have time for that in 2 lectures, or maybe we'll just like get out early and go to the park or something, or we could keep doing more stuff. We have 8 minutes. I'm just going to jump into the beginning of survival with, and again, because this is really going to be high level and conceptual, and we'll just pick up here next time. But This last piece is going to go pretty quickly in the next lecture anyway. The basic idea before we jump in is that Poisson regression is really flexible. We used it to model counts. We can use it to model counts. You can use it to model rates. And so basically you can have person time, you cannot have person time. It doesn't care, right? Obviously, when you don't put person time in as an offset, you're assuming everyone has the same person time effectively, that everyone has the same exposure, but you can adjust for different amounts of exposure, person time, whatever you call it, by using this offset parameter. So it's a flexible procedure for lots of different things. And what we'll talk about is how there's actually this tie-in between the fact that you're estimating a rate in Poisson regression. That ties in kind of nicely to survival analysis, where, by the way, you're also measuring a rate, right? You're measuring this rate of, which is called the hazard, but it's a rate, and it's a rate of the failure. And so you can use that connection to actually do some survival analyses in Poisson regression. Someone very astutely asked, I think it was 2 years ago, why on earth would you do that? Because as you'll see, there's going to be a lot of caveats. It's like, we can do this, but we have to make some assumptions. And then it's more assumptions on the Cox model's assumptions. And there's going to be some very particular reasons why you want to do that. The major one is when you don't have individual level survival and censoring type data. So what I mean by that is, what if you had SEER data on survival in an aggregate way, and you wanted to talk about survival analysis and use survival analysis language, but you don't have individual censoring times, right? You don't have individual covariates that you kind of need to have for a Cox model. The Cox model is always measuring individual kind of experiences, but what if you have aggregate survival data it's truly survival data, and you want to make survival curves, and you want to talk about the hazard ratio? Well, Poisson regression offers you a way to do that because it's totally happy to model these aggregate rate count type experiences. For doing individual level survival analysis, where you're tracking people over time and looking at more nuanced patterns of censoring, probably Cox modeling is going to be the way to go, because you'll see that this is a more restrictive understanding of survival analysis. So that's just the big idea here. And what we're going to basically just talk more about next time, that just to jump right in, we're going to have to zoom back a little bit to like the first day of survival analysis in this course, where we really think about what is the survivor function and the hazard function and all of that. And the survival function, if you remember, is this declining thing over time that goes from 1 to 0, and it's the proportion that are surviving in the population of some disease process. So here is an early AIDS example. And this one, I'm particularly choosing this one because it looks like it might be a good candidate for Poisson survival, as we'll talk about. But basically, it's an exponential decay type function. So we're going to talk about the survivor function and the hazard function. And what we're going to start doing is model the hazard function as Poisson, and then put it into this exponent, and then lo and behold, you have a Poisson survival function. But I think that's going to be cognitively too much on the day before Thanksgiving. So I think we should stop here and have a good break. No lab tomorrow. I think everyone knows that. Enjoy your turkey, tofurkey, and so I'm having a tofurkey. It's actually pretty okay for the people that haven't had it. You just can't have it more than once a year.